I wanted to go out beyond Proxima Centauri. The next closest star to the Earth is Barnard's star that we talked about once before. It's about 6 light years from the Earth. Now, I'm actually trying to plot the motion of a star. I need to do a little elementary physics in order to be able to do that as well. So, for instance, when I'm looking at a star, let's say we're looking at Alpha Centauri. The Centauri group actually consists of 3 stars: Alpha Centauri, Proxima Centauri, and I've forgotten what the designation of the 3rd star is. But these are what's called a ternary system. It's a multiple star system that all the stars are gravitationally bound to one another. Although they're not terribly close to one another, they still move in a grouping. So if we actually looked at this, so let's say we're over here. This is our solar system, or we could say it's the Earth. And then the 3 stars are out here. And I can draw a line to them. There are 2 velocities that I'm actually, from my vantage point, I'm going to see something that appears to be moving this way in the sky. So there's actually, the velocity that I'm going to see, that I'm actually looking at, is the transverse velocity. That is the velocity that's perpendicular to my line of sight. The velocity that's parallel to my line of sight is the radial velocity. So this is radial, and this is the transverse velocity here. So what I actually see, the apparent velocity, looks to me to be the transverse velocity. That's what I'm seeing behind the stars that are in the background here. I'm seeing just the movement in this direction. But I can also get the radial velocity, and I can do that by Doppler shift. Because remember, any motion in this direction is going to produce a Doppler shift of the light. So I can use that to find the radial velocity, and by doing that, I can calculate the radial velocity, and I know what the distance is, at least in this direction. It's 1.3 parsecs. If I look at the transverse velocity, and that's what I can directly measure just by how this appears to be moving in this direction, it's 24 kilometers per second, and the radial I said was 20 kilometers per second. Well, those of you that have had physics realize that this then reduces to a simple vector problem. Then I know that the vector sum of those is going to be out here somewhere, and I can do this using either trigonometry or just geometry. And the vector sum, which is actually the true motion, turns out to be 31 kilometers per second in this direction. So that's how I can use a little elementary physics and what I'm observing to find the true motion of the star. So luminosity is an intrinsic property of stars, sometimes referred to as the absolute brightness of the star. It has nothing to do with how far away the star is or what might happen to be blocking out the starlight. It's just that amount of luminous production that's occurring from that star. Then there's what we call apparent brightness or energy flux. And the apparent brightness is actually directly proportional to the luminosity, but it's inversely proportional to the distance. So if all stars were at the same distance, then we could just say that their apparent brightness was their luminosity. So it wouldn't really make any difference. But all this is really telling us is that we could have the apparent brightness is proportional to the luminosity and inversely proportional to the distance squared. Then you could have 2 objects, same apparent brightness, if one of them had a luminosity that was 100 times as great, but it was a factor of 10 further away, both of those stars would appear to have the same apparent brightness based on this. That when we look at things, the luminosity is not the same as the apparent brightness. So a very luminous star at a great distance can have the same apparent brightness as a less luminous star, which is much closer together. So instead of apparent brightness, astronomers often use something else to indicate the brightness of a star, and it's something that is actually quite old. It was one of the Greek astronomers who actually came up with this. It might have been. It's still something that's being used now, though. We talk about the magnitude of a star. What we can say today, as this has been reformulated, is that when a star changes by 5 magnitude units, that corresponds to a 100-fold change in apparent brightness. So if it's magnitude, the other thing about magnitude is the lower the number, the brighter the star is. So something that is 5 magnitudes greater than something else is going to have 1/100th the apparent brightness, and something that is 5 magnitudes less, has a number 5 magnitudes lower than another star, will have 100 times the apparent brightness of that star. So what we can say is that the faintest star that's detectable by the Hubble or Keck space telescopes has a magnitude of 30. So that's really the best that we can do. The Hale telescope, which is ground-based, is 28. A 4-meter telescope with a charge-coupled device detector is, we can see 26 magnitude stars with that. A 1-meter telescope would be 18 to 20 magnitude stars. A 10-inch scope, 25 centimeters, enables us to see stars of the 14th magnitude. You can see 10th magnitude stars using binoculars. Barnard's star is a 9.5 magnitude star. With the naked eye, the best we can do is about 6 magnitude. Polaris, the North Star, has a magnitude of 2.5. Betelgeuse has a magnitude of 0.8. It's a very bright star. Alpha Centauri's magnitude is 0. Now we actually have negative numbers as well. The magnitude of Sirius is minus 1.5. Venus, when it's at its brightest, is minus 4.4. The full moon is minus 12.5. And the brightest thing that you'll ever see in the sky, the sun, has a magnitude of minus 26.7. Now the stellar temperature, the temperatures of a star, can be estimated from black body curves. The way this is normally done is filters are put into the telescope and they will filter out certain regions of light. So we'll use what we call a violet filter actually, or a blue filter. It passes from 380 to 480 nanometer light. So we'll actually look at that region, and then we'll do a second region that will be what we call a visible filter, and that runs from about 490 up to 540. And by looking at where that would fall on a black body curve, by looking at those two different frequency bands, we're not looking at exact frequencies, but just by looking at the frequency that's being emitted at that particular wavelength, you can get a pretty good estimate of what the temperature of a star is. You can also get some estimate just by looking at the star and looking at its color. There's a color scale that is used, and it's designated O, B, A, F, G, K, and M. So O stars are blue-white in color, and B stars are blue. The temperature of this is 30,000 Kelvin. That would be surface temperature. An example of this star, a star that is a blue-white star, type O star, is Mintaka. Mintaka, remember when we were talking earlier on, we talked about the constellation of Orion. It looks something like that. Mintaka is this star in the belt of Orion. A B star would be the foot star, Rigel. So if this is Mintaka, Rigel is a type B star. Blue, 20,000 Kelvin surface temperature. So better than 3 times the surface temperature of our sun. The star is Sirius, which is sometimes referred to as the dog star, and the star Vega in the constellation Lyra are type A stars. They are white stars. The temperature is about 10,000 kelvins. The star Canopus is an example of an F-type star. It's yellow-white. Temperature is about 7,000 kelvins. Alpha Centauri and our own sun are G-type stars, which are yellow stars, and have temperatures of approximately 6,000 Kelvin, the sun being 5,800. Some giant stars, Arcturus and Aldebaran. These are K-type stars. They're orange. Finally, an example of a red star, Betelgeuse. This was Rigel here. Betelgeuse is over here. This star is Betelgeuse in the constellation Orion. Temperature of the orange star, which is 4,000 Kelvin, and a red star, which is 3,000 Kelvin. So considerably cooler surface temperature on Betelgeuse. Stellar sizes. There's 2 ways of getting the size of a star, either by direct or indirect measurement. Betelgeuse can be measured directly using something called speckle interferometry. Using this particular technique, it's possible to actually measure the angular diameter of the star, and once you know the angular diameter, then you can use some elementary physics, and by doing this we find out that the maximum limit of its radius is 630 times that of the sun. Now, the reason I say maximum limit is because Betelgeuse is what is known as a variable star. So variable stars are stars that their luminosity actually changes periodically. There may be times when the star will appear a little bit bigger than it does at other times. So that would be the maximum size of it. But we know that it's an enormous star compared to the sun. Indirect measurement, on the other hand, involves luminosity calculations using the Stefan-Boltzmann law. And since we know that L equals 4 pi sigma r squared t to the fourth power, from that we can actually deduce another equation, which is r is going to be equal to the square root of L divided by t squared, where t is a ratio of the star's temperature to the sun's temperature. To find t, let's say this is 17,400 K, and the sun is 5,800 K. That's going to be equal to 3.0. Then t, we would put in there, 3 squared would be 9. And L is the luminosity, which we talked about before, and we said we could find the luminosity. It's going to be the luminosity in solar units. In other words, that's how many more times luminous it is than the sun. So if it were 100 times more luminous than the sun, then we would say that that would be the square root of 100, which would be 10. So this would be 1.11 times the radius of the sun. So the answer that you get out of that is actually going to give you the size compared to the sun, how much larger or smaller than it is than the sun. So that's just one way that we can do this. Betelgeuse is what we call a red supergiant, and its radius is 600 solar radii. So just as a point of comparison here, giants are anywhere from 10 to 100 solar radii. So anything that has a radius of 10 to 100 times that of our sun is considered to be a giant. Anything above 100 diameters is what is known as a supergiant, which is what Betelgeuse would fall into that category. And anything smaller than 10 solar radii is considered to be a dwarf, and that would include our own sun. It would be considered a dwarf star based on that designation. Another thing that you should understand about when we're using that O, B, A, F, G, K, M scale that I had before, that there are also numbers that follow that. So frequently when you see a star, it might say 0, 9, and you'll get numbers from 0 to 9. So it's a 10-point scale. It's just a designation that would indicate that the lower the number, the hotter the star is. So if this is a 30,000 Kelvin, that's kind of like the top of that scale. And then a star at 20,000 Kelvin, a B star. So for instance, an 09 is going to be hotter than a B star. Maybe it'll only be 2100. But an 01 would be the hottest that you could get. So if the maximum of the scale, and I don't remember actually whether this is maximum or minimum. That might just be an average value. But 01 is going to be hotter than 02, which will be hotter than 03, and 09 will be the least hot in that scale, but an 09 will still be hotter than a B0 in that scale. If we plot luminosity versus temperature for a lot of stars, we'll get something called a Hertzsprung-Russell diagram. And there is still an ongoing mission. It's the Parcus satellite, which was launched by the European Space Commission some years ago. And it's been doing a lot of this work, and so far has plotted something in excess of 20,000 stars. So we now have a Hertzsprung-Russell, which is also referred to as an HR diagram, sometimes also known as color magnitude diagrams. So basically what we're doing is we're going to be looking at luminosity versus temperature. So this is the luminosity on the y-axis. And on the x-axis, we'll have temperature in kelvins. And if we actually plot this, say, this is kind of backwards the way the astronomers do it. I usually think of going in this direction, increasing, but here we're going to be going in decreasing temperature. So this will be like 30,000 over here, and then this is about 10,000 Kelvin, and then about 6,000 Kelvin, and another point out here at about 3,000 Kelvin. We'll find that most stars will actually lie on a curve that looks kind of like this, something like this. It's going to go like this, and then it's going to curve in like that, and it sort of curves down like that. So there's going to be a region where if we plotted stars in terms of their luminosity and their temperature, we would find that most of them would fall along this spatial area here. And this area here is called the main sequence. Now, not all stars lie on the main sequence. There's also going to be a group of stars that are going to be out here, and there's a region in here, and this is where we find white dwarfs, stars that are called white dwarfs. And then in this region down here, which is still on the main sequence, but in this cooler region down here are where we find red dwarfs. In this region here, we find Barnard's star, for instance. Out here, there's a whole area out here where we're going to find red giants. So the giant stars are not on the main sequence. And we'll learn a little bit later on why that is. Also, there's going to be blue giants that are going to be up in this region here. And then a lot of stars that we can see with the naked eye. Sirius. Sirius A lies up here. The star Altair, one of my favorite science fiction movies. It was called Forbidden Planet. It took place on a planet surrounding the star Altair. Procyon is another. The sun is kind of right in the middle here. The sun's like over here somewhere. Alpha Centauri is there. So this is kind of a very, very rough diagram of a Hertzsprung-Russell HR diagram. And it's something that astronomers actually find pretty useful for a number of reasons. About 20,000 stars have been plotted on an HR diagram, and you can see a picture of a sample plot on page 433 of your textbook. So now we've got a method that we can use to extend the cosmic distance scale. So we know, for instance, that we can go up to 1 astronomical unit using radar. So I can bounce a laser signal off of an object that was an astronomical unit away, and knowing how fast electromagnetic radiation propagates and calculating how long it took for me to get the return echo, I could calculate very accurately what the distance of that particular star was. We can use radar imaging up to about, as I said, approximately 1 astronomical unit. So this is radar. Stellar parallax, which is what we were talking about earlier. Stellar parallax will take us out to a distance of approximately 200 parsecs. So it's a much greater distance. These distances here obviously are nowhere near proportional. So this is taking us to a much greater distance, out to 200 parsecs. But we can actually use another thing that we can use that will enable us to extend the distance even further. So this is stellar parallax. And the next thing is called spectroscopic parallax. But it's really a misnomer because it doesn't really have anything to do with parallax. We don't see something shifting like we did before. This particular technique enables us to see out to approximately 10,000 parsecs. So we can now go much, much further out into the distance than we were able to do before. So in order to do this, what we first have to do is to measure a star's apparent brightness, and then also determine its spectral type. Is it a type O or a type M, whatever it happens to be. So once we know its spectral type and we know its apparent brightness, then we can use the spectral type to find its luminosity. And once we've calculated the luminosity, then we can use the inverse square law to find distance, because we know that the apparent brightness is proportional to the luminosity divided by the square of the distance. So there's also a luminosity designation that is also added to a spectral class to describe a star. So I mentioned before that you could have a type O or M or A, whatever the spectral classification was. Then we would add right after that in the 0 through 9 scale. So we might have an O9 or O8 or whatever. Then we would actually put a class. And the classes are designated this way. A 1A star is a bright supergiant. 1B is just a supergiant. Luminosity type 2 is a bright giant. And a type 3 star is a giant star. Type 4 is a subgiant. And the last one is a type 5. These are main sequence stars and dwarfs. If you have a complete classification of the star, you know its temperature, you know its luminosity, you've got all of this information right at hand. Knowing the luminosity class also helps in determining how far away a star is. Also looking at the absorption lines tells us something about the star's atmosphere. Main sequence stars have very dense atmospheres, and this actually thickens the absorption bands. So rather than getting a very sharp absorption band that you might see that would look like that, you might get something that's much broader for a particular thing, and that would probably give you some indication the atmosphere of that particular star. So these, for instance, a main sequence star would have a thicker absorption band than, say, like a 1b supergiant that was of the same spectral class. If it was a main sequence star, the bands would be thickened. A star's position in the main sequence is determined by its mass and also its composition. The way you would determine the mass is just by the star's effect on another body. So if you're lucky, and it turns out that actually most stars that we know are multiple stars. That is a star that is gravitationally bound. Our own sun is not, but many stars are gravitationally bound to another star in what is known as a binary star system, or there could be a ternary system where there's multiple stars. There's 3 or more stars that are bound together. If we look at binaries, for instance, there's 2 different things that we might see. We have what are known as visual binaries. Now these stars are widely separated, and each star can be independently observed. So in that case, you're just looking at 2 individual stars, and everything that we've said about stars so far, we can determine the parameters for each star individually. But for stars where maybe one star is in the forefront and the other one is too distant to be visually resolved, we can still perceive or understand something about these stars by using Doppler red and blue shift. In other words, the one star is going to cause a wobble on its neighbor, and we'll have that red shift if it's moving away from us, and when it's moving towards us, the light will be blue shifted. So by looking at the spectral lines, that is, rather than the absolute light, we might see if this is a particular band, if it's blue shifted, it's going to move in this direction, and if it's red shifted, it's going to move in that direction. And so from that, we can actually determine something about the motion of those 2 stars, and we can get information in that way. The other thing that we can do, if we're lucky enough and this binary system happens to be such that one star will actually eclipse the other star, from that we can also examine the light curve, the light that is emanating from the 2-star system. So you might see something that looks like this. If you were just looking at the intensity of the light coming out of this, and it was just a single star, we'd see a straight line. So we said we had a straight horizontal line representing the intensity. But if we've got 2 stars together, so we have a line coming out like that. Now, let's say there's one star is considerably bigger than the other one, so there's a straight line, and there's going to be a point where we've got the big star and then the little star here, and that star is actually, the smaller star is actually going to cross in front of this, cross in front of the larger star, and that, if this is the intensity of the light, that will cause the intensity to fall off. Once it passes in front of this, we're going to get a dip in the intensity of the light. We'll get a dip, say, that looks like that, and that's the little star passing in front of the big star, but then that star is going to come out again. So now it's going to be out here. Now this is producing a certain amount of light too. So eventually this star rotating around here is going to fall behind the other star, and once it falls behind the other star, then it's eclipsed. Now it's in the background, so we're not getting its light, so then we're going to see a smaller dip because its light is going to be cut out. And then this pattern will repeat over and over again, this kind of a pattern. So by looking at that, these eclipsing binaries, from that we can get orbits, the masses of the 2 stars can be ascertained. Knowing the mass of a star, we can also estimate its lifetime. The stellar lifetime is directly proportional to its mass and inversely proportional to its stellar luminosity. But because of the relationship that we already have between luminosity and mass, we can actually further reduce this to stellar lifetime being inversely proportional to 1 over the cube of the stellar mass. And that will give us the stellar lifetime. Stellar lifetime, the lifetime of our sun, is approximately 10 billion years. Vega, which is 2.6 solar masses, has an estimated lifetime of 500 million years. And Proxima Centauri, which is only 0.1 times the size of the Sun, has a lifetime of approximately 16 trillion years.